Good morning, all of you. In this session, I am going to explain about a new chapter, that is unit number 4. Okay, in this session, I am going to explain about uh, types of shaft keys used for shafts. A key, first of all, you have to know the fundamental about keys, and also you have to know the function of key. Okay, so this one is a key. Okay, here you can observe this one is a key and this one is a shaft and this one is a hub or pulley. Okay, a key is a piece of mild steel, inserted between the shaft and the hub of the pulley to connect these together in order to prevent relative motion between them. Okay, relative motion between them. It is always inserted parallel to the axis of the shaft. Okay, keys are used as a temporary fasteners. A keyway is a slot or a recess in a shaft and hub of the pulley to accommodate a key. Okay, here you can observe the animation of shaft, key, and hub. So this is the cross-sectional view. Okay, in this cross-sectional view, you can observe this one is a rectangular key. Okay, so this one is a key. Here, this one is a shaft. Okay, here this one is a keyway or groove, key groove. Okay, this keyway is used for inserting this key. Okay, and this one is a hub. Okay, okay. Here this hub also having a keyway. Okay, so this is the assemble view of a key. Okay, so this key is a piece of mild steel inserted between the shaft and hub of the pulley or hub of the gear to connect these two parts together in order to prevent the relative motion between those two parts. Okay, these keys are used as temporary fasteners. Okay, now types of keys. Keys broadly classified into sunk keys, saddle keys, tangent keys, round keys, splines, feather keys. Okay, so these are the important types of keys in our subject point of view. Okay, I will explain one by one. These are the different types of keys. This one is a square key. This one is a flat key. This one is a dowel or a round key. This one is a feather key. This one is a Woodruff key. This one is a gib head key. This one is a tapper sunk key. Okay. So this is the animated view. Here you can observe this one is shaft. Okay. This is the axis of the shaft. Now here you can observe this is a keyway. Okay. This is a key. Okay. Key is a small mild steel piece inserted between the shaft and hub. Okay. Key is a temporary fastener. Okay. Now this is the application of a key. Here you can observe this is a shaft and this one is a pulley or hub. Okay, here this one is key. Okay, here this one is screw. Okay, now this one also a application of a key. Here this one is a motor. This is a motor shaft, and this one is a motor pulley. Okay, here this one is a rope winch. Okay, this one is a rope winch pulley, rope winch shaft and pulley. Okay, this is a belt drive. Okay, so here for transmitting the power from one shaft to another shaft, here we are using belt drives. Okay, so here for minimizing the power losses, we are using a key. Okay, key also used for transmitting the power from one pulley to another pulley. Okay, sunk keys. Sunk keys are the standard forms of keys used in practice and may be either square or rectangular in cross section. The end may be squared or rounded. Generally, half the thickness of the key fits into the shaft. Okay, fits into the shaft key way, and the remaining half in the hub key way. Okay, these keys are used for heavy duty shafts as the fit between the key and the shaft is positive. Okay, sunk keys may be classified as taper keys, parallel or feather keys, and Woodruff keys. Okay, taper sunk keys. Taper sunk keys are square or rectangular in cross section. Okay, uniform in width but tapered in thickness. The bottom surface of the key is straight. Okay, here you can observe the bottom surface of the key is straight and the top surface is tapered. The magnitude of the taper being 1 is to 100. Okay, 1 is to 100 is the taper. Hence, the keyway in the shaft is parallel to the axis and the hub keyway is tapered. Okay, and the taper sunk key may be removed by driving it out from the exposed small end. If this end is not accessible, the bigger end of the key is provided with the head called gib head key. Okay, this one is the example for parallel sunk key. This one is the example for gib head key. Okay, there is no taper for parallel sunk key. Here you can observe no taper for parallel sunk keys. Okay, this one is a gib head key. Okay, rectangular sunk key. Okay, this is a rectangular sunk key. Here, capital T is the diameter of the shaft and W is the width of the key. This is the width of the key and T is the thickness of the key. Okay, this is the cross section. Here, you can observe this is the cross section of the key. Okay, so here W is the width of the key and T is the thickness or depth of the key. Okay, this is the length of the key. L is the length of the key. Okay, here you can observe the bottom surface of the key is parallel. Okay, but the top surface is taper in 1:100. Okay, taper in 1:100. Okay, square sunk key. Here the cross section of this key is a square. Then the width of the key is equal to depth of the key. Okay, so W equal to thickness. Okay, both are equal for square sunk keys. Okay, so this is the example for isometric view of a square sunk key. Now this is the length of a sunk key. Here for square sunk keys also, the bottom surface is parallel, but the top surface is in taper 1:100. Okay, so in square sunk keys, the cross section is square. Okay, for parallel sunk keys maybe square or rectangular cross section. Okay, but here the bottom surface and top surface both are parallel. There is no taper. Okay, here L is the length of the key. Okay, no taper for parallel sunk keys. The cross section of the parallel sunk key maybe square or rectangular in cross section. Okay, gib head sunk keys. This is the isometric view of a gib head sunk key. This is the front view of a gib head sunk key. These are the dimensions. This one is the depth of the key, and this one is the length of the key. Here the total height of the head. The total height of head is 0.75 t. Okay, W is the width of the key. Okay, this one is the side view of the key, and this one is the front view of this key. Okay, from this isometric view you can observe this is the width. This is the width. Okay, this one is width of the key. Okay, and this one is the thickness of the key, thickness or depth of the key. Now this one is a Woodruff key. Okay, okay, this is the isometric view of a Woodruff key. This is the front view of a key, and this one is the depth of key, and this one is the width of the key. Okay, Woodruff keys. Woodruff key is a sunk key in the form of a segment of a circular disc of uniform thickness, as shown in figure. As the bottom surface of the key is circular, the keyway in the shaft is in the form of circular races to the same curvature as the key. A keyway is made in the hub of the mounting. In the usual manner, the Woodruff key is mainly used on tapered shafts of machine tools and automobiles. Once placed in position, the key tilts and aligns itself on the tapered shaft. Another key is a round key. Okay, here the cross section is circular. Okay, so this is the front view of the key. Okay, L is the length of the key. Here you can observe. So here this side, this key having a larger cross section. In this side, this key having smaller cross section. Okay, this is the side view of this key. D is the D is the diameter of the key. Okay, round keys are of a circular cross section, usually tapered 1:50 along the length. Okay, a round key fits in the hole drilled partially in the shaft and partially in the hub. The mean diameter of the pin may be taken as 0.25 D, where D is the shaft diameter. Round keys are generally used for light duty, where the loads are not considerable. Okay, feather keys. A parallel key or feather key is a sunk key, uniform in width and thickness as well as these keys are used when the parts, gears, clutches, extra mounted are required to slide along the shaft. Okay, permitting relative axial movement. To achieve this, a clearance fit must exist between the key and the keyway in which it slides. The feather key may be fitted into the keyway provided on the shaft by two or more screws or into the hub of the mounting. As seen from this figure, these keys are the these keys are of these keys are of three types. Peg. This one is a pegged feather key, and this one is a single-headed feather key, and this one is a double-headed feather key. Okay, pegged feather key. In this in pegged feather key, a projection known as peg is provided at the middle of the key. Okay, the peg fits into a hole in the hub of the sliding member. Once placed in a position, the key and the mounting move axially as one unit. Okay, so this is the front view, and this one is the top view. Okay, T is the thickness, W is the width of the key, and T is the depth of the key. L is the length of the key. Single-headed feather key, single-headed pegged feather key. Sorry, this one is single-headed feather key. Okay, in this key, the key is provided with a head at one end. The head is screwed to the hub of the part mounted on the shaft. Okay, this is the side view. This one is the front view. Okay, here W is the width of the key. T is the thickness or depth of the key. Okay, double-headed feather key. Double-headed feather key. In this, the key is provided with the heads on both ends. These heads prevent the axial moment of the key in the hub. Okay, here two once placed in position, the key and the mounting moves as one unit. Okay, so this double-headed feather key is provided with the heads on both ends. Okay, now this one is a parallel feather key. There is no taper. Spline keys. Splines are keys made integral with the shaft by cutting equispaced equispaced grooves of uniform cross section. The shaft with the splines is called a spline shaft. The splines on the shaft fit into the corresponding recess in the hub of the mounting with a sliding fit, providing a positive drive and at the same time permitting the latter to move axially along the shaft. Okay, this one is the example diagram for a spline case. Okay, this one is a spline shaft. Okay, splined shaft and splined hub. Saddle case. These are a taper case with uniform width but tapering in thickness on the upper side of the upper side. Uh, the magnitude of the taper provided is 1:100. These are made in two forms: hollow saddle key and flat saddle key. Here you can observe this one is a flat saddle key, this one is a hollow saddle key. A hollow saddle key has a concave shaped bottom to suit the curved surface of the shaft on which it is used. Okay, a keyway is made in the hub of the mounting with a tapered bottom surface. When a hollow saddle key is fitted in position, the relative rotation between the shaft and the mounting is prevented due to the friction between the shaft and key. Okay, this is the front view of the key. This one is the side view of the key. Okay, so this is the isometric view of a hollow saddle key. Flat saddle key. Flat saddle key is similar to the hollow saddle key, except the bottom surface of it is flat. Apart from the tapered keyway in the hub of the mounting, a flat surface provided on the shaft is used to fit this key in position. The two types of saddle keys discussed above are suitable for light duty only. However, the flat one is slightly superior compared to the hollow type. Saddle keys are liable to slip around the shaft when used under heavy loads. Here L is the length of the key and W is the width of the key, T is the thickness of the key. Okay. Tangent keys. The tangent keys are fitted in pair at right angles as shown in here. Each key is to withstand torsion in one direction only. These are used in large heavy duty shafts. These are the standard sizes of keys. For design of keys, we are using this table for selecting the standard width and thickness. Standard width and thickness of the key. Okay, corresponding to shaft diameters. These are the shaft diameters. Okay, these are the corresponding width and thickness of the key. In next class, I will explain about problems on shaft keys, and also I will explain how to design a shaft key based on torsion. Here there are different forces acting on keys. In next class, I will explain how to determine the forces acting on the key. Okay. And also I will explain how to design a sunk key. These are the important formulas used in problems. Okay. These all are important formulas for design of keys. Okay. Here P is the power transmitted by the shaft. T is the torque or twisting moment. N is the speed of the shaft. Okay. Now tau is the shear stress induced in the shaft material. Okay. Capital D is the diameter of the shaft. F is the shear force acting on the shaft. T is the torque. Okay. W is the width of the key. T is the thickness of the key. Okay. Now L is the length of the key. Okay. In next class, I will explain how to derive these two cases. Okay. Shearing strength basis and crushing strength basis. Okay. Okay. At the time of problems, we have to use this table for selecting the standard sizes. Okay. This one is saddle key, hollow saddle key. This one is a spline shaft. This one is a parallel feather key. This one is a double-headed feather key. This one also double-headed feather key. This one also double-headed feather key. This one also single-headed feather key. This one is a peg feather key. These all are different types of feather keys. Round key, and this one also round key. This one is a Woodruff key. Woodruff key. This one is a gib head sun key. This one is a parallel sun key. This one is a square sun key. This one is a rectangular sunk key. Okay, these all are the assembled view of parallel sunk key and gib head sunk key. Okay. This is the application of key. Okay. Here we can observe. Here we are using key. Here also we are using a key.